For more videos like this for Compact 211, you can check out Sarai Studies. Link is in the description box below. In this video, I'm going to show you how to construct the table that I use when dealing with octal, hexadecimal, and BCD conversions. Now, the key thing here is to train your brain so that anytime you see the number systems octal and hexadecimal, you think binary. So no matter what they give you, let's say they say, oh, convert this decimal number to octal or hexadecimal, you want to convert this to binary first, and then from binary, you convert to octal or hexadecimal. So how do we get started? Well, it's in the name. Octal means 8. So you just want to write the first 8 numbers you learned in kindergarten. So we start with 0, 1, 2, 3, and so on. So this is 7 numbers plus one more number, that's 8. Now the next thing is to find which binary numbers correspond to each of these octal numbers so that when you get a binary number, you can search for it here. Let's say this is it, and you could say, oh, that's next to 5. So this is 5 and octal. So how do we find this list of binary numbers? Well, it's in the name. Bi means 2, so you're going to start with your powers of 2. And remember, we start on the right. The right side is the right side to start from. And then we fill in our powers of 2 this way. So we're going to have 2, 2, 2, and 2. And we start from here, counting from 0, 1, 2, 3. 2 to the 0, 1. 2 to the first, 2. 2 squared, 4. 2 cubed, 8. And so these are our powers of 2. Now, why didn't I continue? Why didn't I do more powers? Why did I only stay at 4 bits? And the reason why is because with octal, the binary numbers that we're going to get are always just 3 bits. And with hexadecimal, the binary numbers that we're going to get are always 4 bits. And because I want this table to work for both octal and hexadecimal, then I need at least 4 bits. And so octal will be fine with just these 3, and this one will always be 0 because octal will never need the 4th bit. Remember, we start counting from the right side. So 1, 2, 3, and this is the 4th bit here. So we're going to have 4 bits, and now there's no need for memorization. You just ask yourself, how can I make 0 with these numbers right here with these place values? Well, I will need 0 8s, 0 4s, 0 2s, and 0 1s. I'll need none of these so that I can have nothing, just 0. To make 1, I'll just need 1, 1, and I'll need none of these. To make 2, I'll just need 1, 2, and then none of these. To make 3, I'll need 0 8s, 0 4s, 1 2, and 1 1, because 2 plus 1 gives me 3, which is the number I'm trying to represent. To make 4, I'll need 0 8s, because if I did 1 8, then I wouldn't have 4, I would have 8. And then I would do 1 4. And because I already have 1 4, I got the number I wanted, I don't need any of these. So 0 2s and 0 1s. To make 5, I'll need 0 8s, 1 4, 0 2, and 1 1, because 1 4 and 1 1 together make a 5. 4 plus 1 is 5, which is the number I want to represent. To make 6, I'll need 0 8s, 1 4, 1 2, and 0 1s, because 1 4 and 1 2 together make a 6, which is the number I want to represent. And to make 7, I'll need 0 8s, 1 4, 1 2, and 1 1, because 1 of all of these, if I add them together, 4 plus 2 gives me 6, plus a 1 gives me 7, which is the number I want to represent. So this is our binary to octal table. Now notice how all of the binary numbers that correspond to each of the octal numbers never used up the 4th bit, because again, all of the binary numbers that you're going to get to convert to octal are just going to be made up of 3 bits. So you'll only ever need 3 of them. So it's never going to use up a 4th bit. It's always going to be 0. And again, the reason I added the 4th bit is because with hexadecimal, all of the binary numbers you're going to get here are going to be made up of 4 bits. And because I want this table to contain both of these conversions, I want everything to look consistent, so I'll be doing 4 bits. So the idea is if I give you a binary number such as this one and I ask you to convert it to octal, you're going to make groups of 3 starting from the right side, because the right side is the right side to start from. So starting here, this is one group of 3 and this is another group of 3. And you ask yourself, okay, what is 1 0 0 in octal? Well, you use your conversion table. You try to locate 1 0 0. I see 1 0 0 here. What is that in octal? It's 1. So this becomes 1. Then you move on to the next group. What is 1 0 1? Well, I try to locate it. Oh, I see that it's here. 1 0 1. What is that in octal? It's 5. So this number in binary, it's 51 in octal in base 8. Now, what if I want to convert this binary number into hexadecimal? Well, I'll just make groups of 4. Now, why do we make groups of 3 and 4? Well, octal means 8. So you just ask yourself 2 to the what is equal to 8? 3. That's why you make groups of 3 with octal. Hexadecimal. Hexa means 6. Deci means 10. 6 plus 10 is 16. This is base 16. Ask yourself 2 to the what is 16? 4, which is why we make groups of 4. That's it. So starting from the right, because the right side is the right side to start from, your first group of 4 is these right here, which I actually don't see anywhere here because this is the octal conversion table. We still haven't done the hexadecimal one. So the idea with hexadecimal is that it goes from 0 to 9, and then once it reaches 10, the alphabet starts. So instead of 10, you do A, and then you do this all the way to F. So we're going to do 0 to 9, and then A, B, C, D, E, and then F. Now the idea is these binary numbers correspond to these hex codes. But what binary numbers correspond to these hex codes? Well, we just continue the whole thing. So now I think of these as decimal numbers, and I just keep going. So 8, 9, 10, 11, 14, 15. Now you do here what we did here. How do we make 8 with these place values? Well, I'll just have 1, 8, and I'll have 0 of everything else. How can we make 9? Well, I'll have 1, 8, 0, 4, 0, 2s, and 1, 1. Because 8 plus 1 is going to give me 9. How can I make 10? Well, I'll have 1, 8, 0, 4s, 1, 2, and 0, 1s. Because if I have 1, 8, and 1, 2, 8 plus 2 gives me 10. To make 11, I'll have 1, 8, 0, 4s, because if I do have a 4, then 8 plus 4 is 12, and that goes over 11. 1, 2, so now I have 8 plus 2, that's 10, and then 1, 1. So 10 plus 1 is 11, the number I want to represent. To represent 12, I'll have 1, 8, and 1, 4, because 8 plus 4 is 12, and then 0 of everything else. To represent 13, I'll have 1, 8, 1, 4, 0, 2s, because if I take a 2, I'll be over 13, and then 1, 1. So one of these numbers, 8 plus 4 is 12, plus 1 is 13, which is the number I want to represent. To represent 14, I'll have 1, 8, 1, 4, I already have 12, and then 1, 2, so these three numbers added together gives me 14, and then 0, 1s. And then finally to represent 15, I'll have 1, 8, 1, 4, so I already have 12, 1, 2, so 12, 13, 14, and then 1, 1. So 14 plus 1, that's 15, which is the number I want to represent. So this red box is our hex conversion table. These are our hex codes and the binary numbers that correspond to these hex codes. So starting from here, if this is the first group I'm looking for, 1001, well, 1001, I see it's here, and its corresponding hex code is 9, so this becomes a 9. And then the other group is 01, and then because we know it's supposed to be 4 bits, there's nothing there. How do you represent nothing with zeros? So you're really looking for 0100. So 0100 is right here. What hex code does it correspond to? 2. So this here is going to be 2. So we say that this binary number in hexadecimal is 29. Now let's say I want to convert the same number in binary to BCD. Well, with BCD, you need to start with the decimal version of the number. So we're going to have to go from binary to decimal. So how do we do that? Well, I'm just going to write the number in binary, and then I'm going to do my powers of 2. So 1, 2, 4, 8, 16, 32. And then I'm just going to add wherever I see 1. So I have 132 plus 1, 8 plus 1, 1. So this is 40 plus 1 is 41. So this is 41 in base 10 in decimal. Now all you have to do is look at each digit individually and convert it to its BCD code. Now here's the idea. Because every number in decimal can be written with the digits from 0 to 9, so when you have a keyboard, do you notice that you only have the numbers 0, 1, 2, 3 all the way to 9? You don't have 10, you don't have 11, because you can make every single number in the world with just these digits, 0 to 9. So because we're only ever converting individual decimal digits to BCD code, you're only ever going to convert either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. In this case, we're converting 4 and 1. So because we're only going to be dealing with the digits 0 to 9, then we're just going to be looking over here from 0 to 9. This is our green box. This is our decimal numbers, and this is our BCD code. So you would search for 4. What is 4's BCD code? It's 0010. So 0010, and then you search for 1. What is 1's BCD code? It's 1000. 1000. And that's it. This is 41 in BCD.